student, I Soumen sir, lecturer in mechanical engineering. Today we derive bending equation. Chapter name bending stress in beam under strength of materials. Derivation of bending equation or flexural formula. If a simply supported beam support on both ends and a point load act at center, the beam bends into a curve. We take a small length of bend under load NL equal to neutral layer. This length makes an angle theta at center O. Here radius of NL neutral layer is R. This is R. Neutral layer neither compression or tension. The length of NL before loading and after loading are same length. Above neutral layer NL, compressive stress increases gradually. Topmost layer, this is the topmost layer, maximum compressive stress, maximum compression. Below NL neutral layer, tensile stress increases gradually. Bottommost layer, maximum tensile case, that means maximum tension in the bottommost layer. Now we take a layer GH. We take a layer GH below the neutral layer NL. GH distance Y from the neutral layer NL. This is the Y. Let us consider a small length of a beam bent under load. Let F equal to stress due to bending at a distance Y from neutral axis NA or neutral layer NL. Neutral axis NA shown in cross section, that means in side view it is shown in neutral axis. Y is the distance of layer in which bending is considered from NA, in which bending are calculated. I equal to moment of inertia of the beam section, that means beam cross section. Beam cross section may be square, may be rectangular. So I equal to mi of the beam section about NA. R equal to radius of curvature of NL neutral layer of the deformed beam. M equal to bending moment. Here we calculate bending moment in this layer GH, distance from Y from the neutral layer NL, E equal to Young modulus for beam material. Now consider a layer GH at a distance Y from neutral layer NL, distance Y. Here increasing length, the GH length in initial position, GH length and neutral layer NL length are equal, but after bending GH length increases, increasing length equal to GH minus NL. Original length of the GH previously before bending, original length GH equal to NL, so original length of GH equal to NL. We know strength means increase in length by original length. Here increase in length GH minus NL, original length NL. Okay. Now from trigonometry, the length of GH arc length equal to R plus Y, distance from O, R plus Y into theta, minus NL equal to NL length equal to R theta. This radius is R theta minus NL R theta equal to Y by R. This is equation number 1. Again, from Hooke's law, we know E equal to, from Hooke's law, we know E equal to Young modulus equal to F by E. E means stress by strain. তাহলে from Hooke's law, strength equal to ছোট হাতের E equal to F by capital E equal to Young modulus. This is equation number 2. Okay. Now from equation 1 and from equation 2, we compare strain equal to Y by R, and from Hooke's law, strain equal to F by E, Young modulus. So from equation 1 and 2, F by E, capital E equal to Y by R. Now interchange F by Y equal to E by R. This is equation number 3. Now for exam purpose, we see the equation number 3, F by Y equal to E by R. Here, if we consider the stress above the NL, above the neutral layer, there is a compression. So FC by YC, FC compressive stress, distance from neutral layer, above neutral layer, YC equal to E by R. Again, if we calculate any layer from neutral layer NL below the neutral layer, Yeah, then below the neutral layer, tensile stress gradually increases. So any layer below the NL, Ft equal to tensile stress, any layer from below the NL, Yt equal to distance of this layer below the NL equal to E by R. From this, we can say Fc by Yc equal to Ft by Yt. This is compare. Now, we can also say Fc by Ft, compressive stress by tensile stress equal to Yc. Yc means distance of layer above the NL where we consider that compressive stress. Yt equal to distance of layer where we consider the tensile stress. Okay, now we take the cross section of the beam. Cross section of the beam B equal to width of the beam and depth equal to D. In cross section, NA equal to neutral axis. In front view of the beam, NL neutral layer, and in side view cross section, where cross section we shown, they are NA equal to neutral axis. Now a elementary strip where we consider stress, bending stress, distance y from neutral axis, width of the elementary strip dy. Now let us consider an elementary strip of thickness dy and distance y from neutral axis of the beam section. Y is the distance from neutral axis. Area of the strip, B into dy, area of the strip B into dy. Now we know from previous equation number 3, equation number 3, we know F by Y equal to E by R equal to E by R. So F equal to E, so stress in this area, F equal to E by R into Y. Okay. Again, we know stress means force by area. Stress, what is stress? Stress equal to force by area. So force on the area equal to stress into area. Here stress, this is the stress, this is stress, and this is the area. This is stress and this is the area. So force on this area equal to E by R into Y into area B into dy. Now we know moment of this force about NA. Actually we calculate area moment, the force, this is the force into distance. So E by R into B into dy into this y and this y square. This is the moment of this force about Na. This is the moment of about Na only for this elementary strip. Now we calculate entire moment of entire section. Then we calculate moment of entire beam section about Na, capital M, equal to E by R summation of B into dy into y square. Okay, summation or integration. We know summation of B into dy into y square equal to moment of inertia of whole cross-sectional area about Na equal to I. Okay, now summation of B dy into y square, here this is I, this is the I moment of inertia. Then from this portion, therefore M equal to E by R into I, or M by I equal to E by R. This is equation number 4. In previous equation, equation number 3, F by Y equal to E by R, and equation number 4, M by I equal to E by R. Comparing or combining equation 3 and equation 4, M by I equal to F by Y equal to E by R. This is the bending equation. This is the bending equation. This is the bending equation, or sometimes it is called as flexural formula. Okay, it is clear, my student. Thank you.